Yeah, Patrick Cheridito, now in ETH Zürich, and he moved in September from Princeton, so we are happy that he's in Europe, so we have more chance to overlap and meet. Patrick has given many contributions in mathematical financing, risk measurement, and equilibrium and BSDs, and today he's going to talk about variable annuities with high watermark withdrawal benefit.
Okay, thanks so much for the introduction, and thanks for having me here. So this is work on variable annuities with high watermark withdrawal benefits, and I started it while still back at Princeton with a student at Princeton, Pei-Chi Wang. And so one reason why these contracts became popular is that in many countries there was a change from defined benefit to defined contribution pension plans, and this shifted exposure to income and longevity risk from employers to the employed. So variable annuities with protection features have gained popularity in several countries. And so I'm kind of new a little bit to this literature, but in the literature on this, there is this notation: VA is variable annuity plus GMXB is guaranteed minimum something benefit. Okay? And then so roughly, I mean, there is a whole variety of these contracts, but then roughly you can categorize them into 4 categories. One is guaranteed minimum death benefit, in which you invest money in an account or something, and then you get a guaranteed amount if you die, or your dependents get a guaranteed if you die, an amount if you die. Then there is guaranteed minimum accumulation benefits, guaranteed minimum income benefits, and then the type of contracts that I want to concentrate on today are guaranteed minimum withdrawal benefits, which are contracts that allow you to withdraw money from the account every month or every week or every 6 months or every year, depending on the specifics of the contract. So roughly the geographical picture of these contracts is like this, and also this picture is 3 or 4 years old because I stole it from the presentation of a practitioner that I found on the internet, so I don't really know all the precise numbers myself, but roughly the largest market is in the US, and they also have the largest variety of crazy contracts that they offer over there. And then there is a big market in Canada and Japan, and then there is somewhat of a market in Europe, and then in other countries in Asia and in Australia. So I'm in Switzerland right now, so why would I care so much about these contracts? Well, first of all, they're mathematically interesting, and also there are international insurance companies in Zürich that have exposure to these contracts in Japan and the US, for example, and I'm assuming the same is true here. Okay, and so this is from a web page from Vanguard, which is a US investment management company, and they're offering a variety of these contracts. And this is one of the pictures they show, and this is just to illustrate the main feature of the contract that I'm going to discuss today, which is this high watermark benefit base. So what you can withdraw from this contract doesn't depend on how much money you have in the account right now, but it depends on the high watermark, which is the running maximum of this contract. Okay, then it depends on how frequently you update the high watermark. So in this contract, it's yearly. And so it's illustrated with these locks here. So this is the white line is the evolution of your account. But then at these dates, you look at how high was the account then, and then you lock in this high watermark. And even if the account falls after that, you will still be able to withdraw money according to the high watermark, okay? Okay. So the plan for this talk is formulate a tractable model for such a contract with a high watermark withdrawal benefit, and I'm going to do it in continuous time, okay? Because this will give me tractability, and I will be able to answer some of the questions explicitly. So this will be not such a good model if you have a contract that updates the high watermark only every year, but there are also contracts that update the high watermark every week, and we even found a contract with Vanguard that updates every day. Okay, so then if you do this in continuous time, it's not such a bad model. We want to characterize the superhedging price and the worst case policyholder behavior through a Hamilton-Jacobi-Bellman variational inequality. And also I will always talk about the worst case policyholder behavior and not the optimal policyholder behavior or rational policyholder behavior, because I'm taking the point of view that I don't really know what's optimal for the policyholder or what's rational for the policyholder, because there might be things going on in the life of the policyholder. The policyholder might lose the job, or there is something that needs to be fixed in his or her house. That's why he or she needs money right now, and I don't really know what's going on there. So I'm going to look at this contract from the point of view of the issuer, which is an insurance company, for example. I'm going to talk about the worst case policyholder behavior, which is the worst case for me as an issuer, okay? But then I'm not saying if the policyholder doesn't behave like this, that's not rational or that's not optimal, because again, I don't really know what's optimal for the policyholder. Once I figure out what the worst case policyholder behavior is, I can derive a hedging strategy to hedge against that, and then we will also develop a numerical scheme. So we do this to try to gain insights into how the price depends on the risk-free rate, volatilities, and fees that are embedded in the contract. What the worst case policyholder behavior is from the point of view of the issuer, how the insurance company should set the fee structure, and also an issue with this contract is surrender behavior or lapse behavior, okay, which is many of these contracts can be surrendered early by the policyholder, and many times there isn't even a penalty for that, and it's a risk to the issuer. And so what we're going to discuss here is how to penalize early surrender to disincentivize the policyholder from doing this. Okay, then in the real world, they might still be doing it, but the hedging strategy that I'm going to derive will cover me against early surrender. Okay, so for dynamics of the underlying mutual fund, I'm just taking the simplest model, which is the Black-Scholes model, since the contract is going to be complicated enough. But then if you like, you can extend this to stochastic volatility or regime switching. I mean, actually, we have a version of this paper where we also do a regime switching model on this, because the contract is going to be long. It's going to be 15 or 20 years, for example. Okay, but then for this talk, it's the underlying mutual fund is just a geometric Brownian motion with some drift mu and some Brownian motion w, but then I'm going to change immediately to the risk-neutral world, and I'm going to replace this Brownian motion w by another Brownian motion b, and the drift by r, which is the constant risk-free rate. Okay, sigma is the volatility as usual. And then there is going to be a market filtration, which is generated by S. Okay. And then for this contract, again, so these contracts exist with fixed maturity, or they exist for life, which means they run as long as the person lives. Then you also have to specify, so what I'm going to consider here is a fixed maturity, which is 10, 15, or 20 years. And also to get rid of mortality risk here, I'm just going to say if the policyholder dies in this period, the policy is just transferred to a beneficiary, okay? So I could also in this model specify a death guarantee, which would be some that is going to be paid out if the policyholder dies during the contract, but then I would have to introduce a death time, and then I have to integrate over the distribution of this death time, but I don't want to do this here, so I'm just going to say the contract is going to be transferred in case of death, and so this is just going to be a fixed maturity contract, capital T, 15 years, for example. Then at time t equal to 0, the policyholder starts the contract by making a lump sum payment P, which I'm going to decompose into P1 and P2. Okay. And the issuer sets up an account A by investing P1 in the mutual fund, which behaves according to this exponential Brownian motion, and then keeps P2 as an upfront premium. And then typically in these contracts, P2 is 0. Okay, so the whole initial lump sum payment by the policyholder will be invested in the underlying account, but then there will be running fees, okay? And I'm also going to introduce these running fees, which are Q. But I also want to keep this P2 for me as an option to maybe collect this upfront premium. Otherwise, maybe I'm selling the contract too cheaply. Okay. So the P is the upfront premium. And then in addition to that, there will be periodic fees that you have to pay. And these will be proportional to the current account value, okay? And then again, I'm going to decompose this Q into Q1 and Q2. And then how it works is Q2 is an insurance fee for the insurance company, which is a fee that you pay for the guarantees that are embedded in the contract. And then Q2 is a management fee that the insurance company is paying to the manager of the underlying fund. Okay. Then the holder chooses a withdrawal rate and the surrender time theta. Okay, so theta is going to be a stopping time at which time the holder of the policy is going to decide to surrender the contract, and W is the rate at which the holder of the contract is going to decide to withdraw money. So a geometric Brownian motion can never hit 0, but this A can hit 0 because it's a geometric Brownian motion, but I'm subtracting all these withdrawals and I'm subtracting the fees, so this thing can hit 0. And if it hits 0, I'm just going to freeze it at 0. Okay? So then the dynamics of A is this, okay, which is all the terms coming from the geometric Brownian motion. Then the Q here is the periodic fee that has to be paid, and W is the withdrawal that the policyholder makes from the account. The account starts at P1, which is the part of the lump sum payment that was invested in the account. And if it hits 0, I'm just going to freeze it at 0. Okay. Then there is also going to be private information. So private information is private events such as changes in employment status, health or family situation. And I'm going to model this with the filtration G. What I'm going to assume is that the big filtration H generated by F and G is F plus something which is independent of F under my pricing measure Q. Okay, so I'm not exactly assuming F and G are independent, but I say H is F plus something which is independent of F. I don't think that's a really strong assumption. I'm going to need it. Then the high watermark is just the running maximum of the account A. Then the withdrawal rate must be adapted to the big filtration because it's the withdrawal rate according to which the policyholder withdraws. And then there is going to be constraints and fees on the withdrawal. Okay, so you're not going to be allowed to withdraw whatever you want, but typically how it works is there is going to be a fraction alpha, which is, for example, 5%, and you will be able to withdraw between 0 and 5%. From this account, and you're going to be charged fees according to some rate L1, and typically this rate L1 is 0. So if you withdraw within 0 and 5%, you can withdraw and you don't pay any fees. Okay. Then there is a higher threshold beta, which might be 10%, and if you withdraw between 5% and 10% of the high watermark, you can still do that, but then you're going to be charged a real fee, which might be 5% of what you withdraw. Okay? And then on top of that, there is also going to be a constraint on the total cumulative withdrawal that you're allowed to make, which might be 100% of the high watermark or 90% of the high watermark. Okay. And the guaranteed withdrawal means even if the account hits 0, you can still withdraw because the high watermark might be 100. The account now is 0, but then you can still withdraw, and that's the problematic case for the issuer, because as long as the account is alive, I can pay withdrawals from the account, but if it's 0, I have to start paying it out of my pocket, and I have to hedge against this case. Okay. And then the income rate to the policyholder is this whole expression here. It doesn't really matter so much how it looks like, and so it's a complicated contract, but it's still, I mean, if you look at the actual contract, so we downloaded one of those, it's much more complicated. It's 150 pages of explanations, okay? So this is slightly easier than the 150 pages, but is it clear to everybody how more or less this contract works? Okay. Okay, one more thing. So the holder can surrender the policy at the stopping time. And for many contracts, there is actually no penalty. So what happens if the policyholder decides to surrender the contract is that the policyholder just gets the current account value 80 back. Okay. But then here we're going to study what happens if I penalize early surrender. And so I'm going to penalize with h theta, which is a fraction that depends on the time when you surrender. And then h theta, this fraction, which might be 1, 2, or 5% of the current account value, is kept by the issuer as a penalty, and the rest is returned to the policyholder, which means g theta or eta t is returned to the policyholder. H is some function that depends on time and is a fraction. It's between 0 and 1, and g is just 1 minus h is the remaining fraction that is going to be returned to the policyholder. Typically, h at the maturity is 0, which means if you wait until maturity of the contract and there is something left in the account, then just what's left in the account is returned to you. And then what we're going to study is penalty schemes of the form HT is a constant of time to maturity. Okay, so the earlier you surrender the contract, the higher of a penalty you have to pay. Okay, so policyholder behavior is now completely specified by the withdrawal strategy and the early surrender time. Now what I'm going to, so as I said earlier, I'm going to look at this problem as from the point of view of the issuer. I'm going to try to figure out what is the worst case behavior of the policyholder. And to figure that out, and it's not apparently clear quite yet why I'm doing this, but what I'm doing is I'm writing all the cash flows that I, as an issuer of the contract, have to make. I'm discounting them by R, and then I'm taking expectation under the risk-neutral probability measure, okay? And then if you keep track of all the terms, so this is like payments that you have to make due to withdrawal. So F was withdrawal minus the fees that you charge for withdrawal. This was the penalty that you get if the policyholder decides to surrender early. That's why it's with a minus sign, because it's going to be incoming cash flow. This is also with a minus sign because it's the periodic fee that the policyholder pays to you. And then these are other terms which are also related to the fees, okay? But it doesn't matter so much. But what I'm doing is all the cash flows that I have to pay to the policyholders, I'm going to discount them with R, and I'm going to take expectation on the Q. And I'm calling this DA0, okay? And then, since this looks complicated, I'm turning this around, okay? And I'm writing A0, plus DA0 as EA0, where EA0 now is the discounted cash flows going to the policyholder, plus what the policyholder receives if he or she decides to surrender the contract early. And then you will have an additional term here, which will be the fees that have to be paid to the manager of the portfolio, okay? And so this now looks like an optimal control problem from the point of view of the policyholder, okay? And in some papers, this is called optimal or rational policyholder behavior. But I call this worst case policyholder behavior because it corresponds to the worst case for me, okay? And then how the policyholder actually will behave, that I don't know. But I'm saying the policy is correctly priced from the issuer's perspective if DP1 is this additional upfront payment that I'm asking for, or equivalently EP1 is P1 plus P2. Okay. Okay, we still don't quite know why I'm discounting these cash flows with R and I'm taking expectation on the Q, but the reason for this is this will be the smallest super replication price, which allows me as an issuer to super replicate this contract in the worst case. Okay. And to show that, first we'll have to solve this stochastic control problem here, which now is a combined optimal control and stopping problem, right? Because I have a control W here, and I have a stopping time theta in here. So I'm going to solve this problem, and then I'm going to build on that. So the good news is, so in this soup, the W and the theta are allowed to depend on the big filtration, which is the combination of the market information plus the private information. The good news is you can show that the soup is attained for strategies W and theta that actually only depend on the market information. So I, as an issuer, will be able to solve this problem without knowing what's going on in the private life of the policyholder. The bad news is the optimization problem EA0 is not Markovian because it depends on the running maximum, and to know the running maximum, I have to know the whole path of the processes involved in this problem, right? But then there is an easy way out of this, and it's just add more state variables. And so what I'm going to do is I'm going to keep track of the current account value, which if I at time t started from A, and the policyholder strategy is W evolves like this. And then I'm going to add the running maximum just as another state variable to the problem. And then I also have to add the cumulative withdrawals as another state variable to the problem, because the problem will depend on how much I have already withdrawn, because there is a constraint on total withdrawal. Okay. So this gives me 3 state variables, and then I can write the optimal control problem starting from every time given that the current account value is A, the current running maximum is M, and the current cumulative withdrawal is C, as this expectation here, okay? Now I allow W and theta, which are the withdrawal strategy and the early surrender time, to be adapted only to this small filtration generated by my underlying Brownian in motion B, okay? And I justified before why I can do that. So if I can solve this whole problem for every T, A, M, C, then I can plug in 0 for T, and then this gives me the price of the contract that I'm interested in. Okay, so now we're just going through a PDE characterization of this value function U, and then, so this is going to be a variational inequality, because there is going to be a free boundary, because there is this optimal stopping time that I don't really know when it is, okay? So the first thing that you notice is the value function is always bigger than what you would get if you would stop immediately, because it will be this fraction GT of the current account value A, okay? So you always have this inequality here. Then on the continuation region, you will just satisfy this second order parabolic PDE, where the Hamiltonian is this term here, okay? So this is standard optimal control if you do it through a Hamilton-Jacobi-Bellman approach. Okay, what I should mention is so here you have like the usual terms which are just coming from the dynamics of your underlying account, and then here you have a max which is coming from the fact that you're allowed to maximize this over withdrawal strategies. And what you notice here is what you maximize is piecewise linear, okay? Because this f function was like piecewise linear because if you're going to withdraw between 0 and 5% of the high watermark, you pay a fee of this or that. And if you withdraw above that, you're going to pay a fee which is different, but it makes this f here piecewise linear. And this term is also linear in W. And if you're going to maximize this over W in this interval, it's going to be, the maximum is going to be attained at one of the breakpoints. Okay, so if you maximize this, you only have to check among 3 different values. The maximum withdrawal strategy will always be either withdraw nothing, withdraw 5% of the high watermark, in which case you pay no fees, or withdraw at the higher rate at which and pay more fees than that. Okay. And okay, just to jump ahead to the numerical situation. So the typical picture will look like this. So you will have regions for fixed time in your state space, where you will withdraw at maximum speed, intermediate speed, or 0, and then there will be a region where you will surrender the contract. Okay, so this is I'm just jumping ahead to give you a picture of how the strategy looks like. So far, everything was pretty standard. So where the problem becomes a little bit non-standard is with the boundary conditions, okay? Because you have now this PDE in 3 space dimensions and 1 time dimension, and you will have to introduce boundary conditions to solve this problem. So the terminal condition is clear. It's just if you wait until terminal time, you will get the fraction G of capital T of the remaining account value. Then there is a boundary at C equal to 0, which means you have not started to withdraw. Okay, at this boundary you will have what is called a state constraint. What it means is you just solve the Hamilton-Jacobi-Bellman equation at this boundary. Then the boundary C equal to gamma m means you have exhausted your withdrawal. You're not allowed to withdraw anymore. Okay. Then you solve the same Hamilton-Jacobi-Bellman equation there, except the Hamiltonian becomes H0, which is this guy here, which is the same as before, except you're missing the term where you maximize over W because you're not allowed to withdraw anymore. Okay. So, and this just becomes like a plain vanilla linear second order PD. Then the A equal to 0 boundary is the boundary where the account value has hit 0, and I'm going to freeze it there, okay? And then the problem for you becomes a deterministic withdrawal problem, because nothing is going to move anymore. The account value still will stay at 0. The high watermark will stay wherever it is, because you will never be able to push it up higher again. And so you're just going to solve this deterministic optimal control problem, which you can solve almost explicitly. Okay, but the value of this problem will give you the boundary value for this A equal to 0 boundary. And then the last boundary will be on the diagonal between your account value and the high watermark. Okay, so the account value can never go above the high watermark. If the account value goes above the high watermark, you just push the high watermark up. So you will have a boundary at A equal to M. And so the question is, what is the boundary condition at this boundary? And it turns out that you will have like this oblique derivative condition there, that the derivative of the value function in the direction of the high watermark has to be 0 there. And so maybe for those of you who are familiar in stochastic control, I give an intuitive argument why this has to be the correct boundary condition there, but then you can also verify it rigorously if you want to. But what's the intuitive explanation why this is the correct boundary condition on the diagonal. So what you can do is you can approximate the high water mark by averaging the account value from 0 to t to the p and then taking 1 to the p. And for p going to infinity, this will approximate the max. Okay, and then in your stochastic control problem, you can replace the high water mark by this approximation, and then you will receive a standard Hamiltonian, which I call HP. Okay? And it will look the same as before, so you will have this sup term here where you maximize over the withdrawal strategy, plus all the other terms, plus you have one more term here, which is coming from the approximation, okay, which will be m over p, and then a divided by m to the p times the derivative of a in the direction of the high water mark. So now the argument is if you send p to infinity, and then this term here goes to infinity if a is bigger than m, okay? Otherwise it goes to 0. And so to satisfy the equation that this is equal to 0, if this one term explodes, that can only happen if the derivative which you use to multiply this term is actually 0, okay? So this is an intuitive reasoning why you have this kind of strange or non-standard boundary condition on the diagonal. Okay, so having written everything or explained piece by piece, I can write everything on one slide. And so then this is a result that you can show that U is a weak solution in the sense that it's a viscosity solution of this HJB variational inequality. So you have the max between these two terms is 0 if you're inside of the domain. Then the max between these two terms is 0 if you're on this boundary of the domain, the C equal to gamma m. And this is the terminal condition. This is the condition phi was the solution to my deterministic control problem. So this is the boundary condition at the boundary A equal to 0. And this is my boundary condition on the diagonal. Okay? So that's good, except that's a nonlinear parabolic PDE with 3 space dimensions, and also the domain is unbounded, and it has unusual boundary conditions. So luckily this whole problem scales, okay, because everything depends proportionally on the high watermark. So I can normalize everything by the high watermark. And then you receive, so what you do is you introduce this new function v, and okay, you show that u is actually mv, and then a normalized by m and c normalized by m, okay? And then this v is a viscosity solution of this system of equations which looks similar to before. Here you have even a stranger boundary condition which mixes derivatives with respect to x, y, and v itself. But the good thing is, so this now is still a nonlinear parabolic PDE, but it's only 2 space dimensions, and it's also a bounded domain in space. It's just a rectangle in space. So there is still a free boundary, but and there are still even more unusual boundary conditions. But now, I mean, I can solve this problem. It's not easy, but I can solve this problem numerically. Okay. So if I can solve this problem numerically, the worst case withdrawal strategy will be given to me by the optimizer W, which optimizes this function here at every t, a, t, m, t, c, t. The worst case surrender time will be the smallest t, such that the value function at t, a, t, m, t, c, t is equal to g, t, a, t. And the issuer can set the penalty for early surrender, or equivalently the fraction that the policyholder will receive if he or she decides to surrender early, so that the worst case policyholder never surrenders early. Okay, so again, in reality, a real life policyholder might still surrender early, but then I will be covered against this case. So what you can show if you do this in continuous time, a sufficient condition for the worst case policyholder never to surrender early will be that the derivative of G is bigger than this quantity here. And if you are staying in the class of penalty schemes for early surrender, which are this proportional constant times time to maturity, this is satisfied if you choose this constant kappa bigger than the running fees Q1. Okay. Hedging. So the issuer can superhedge the contract now by trading in S and the money market account. And okay, so I'm assuming that I'm collecting P for this contract, which is the fair value. And then I'm also assuming, and here I make an assumption, and it's not 100% clear whether that can be done analytically because it's related to regularity results of PDEs. And the PDE I have here is degenerate because I only have a second order term in the direction of A. And, but what I'm doing is I'm just assuming I have the regularity that I need. And if I look at the pictures from my numerical simulations, I have this regularity, okay? And so the regularity that I need here is I need that the value function is C11, which is once differentiable, and the first derivative is Lipschitz or locally Lipschitz, okay? And I'm also assuming that it's C2 on each of the subregions. Okay, let me maybe just go back to the picture that I showed you. So there are these different regions which correspond to not withdrawing at the intermediate level or withdrawing at full speed, and then early surrender of the contract. And from the picture already you see that everything looks pretty regular. So what I'm assuming is, so since here you keep the W fixed, the PDE you're looking at is just a linear second order PDE. So I'm assuming on this region it's C2, okay? I'm assuming on this region it's also C2, here it's also C2, and here it's actually equal to GTA, okay? So I know what the obstacle is, okay? That's not a problem. Then what I have to assume that it's differentiable across these regions, okay? And the second derivative maybe jumps, okay, but not more than that. The first derivative is not allowed to jump, okay, but the second derivative typically in situations like these will jump. But then if you have this, you can still write an Ito formula, and the Ito formula will be of standard form, okay, so there will be no local time terms, nothing, okay. So if you have these assumptions, you will have Ito's formula in standard form, okay? So I'm going to write it. So I have derivative with respect to T, A, M, sigma, and the second derivative with respect to A. So this term will go away by my boundary condition, okay? Because M can only grow if A is equal to M, okay? If A is pushing up M. And so if this grows, A is equal to M, but there I had the boundary condition that UM is 0. So this term goes away immediately. And then I'm using the PDE for this term here. And then I'm writing that U is smaller or equal. So now this depends on whether W is the worst case strategy or not. So if it's the worst case strategy, I'll have an equality here. Otherwise, I will have an inequality. And then I'm rewriting these terms. And so then basically what this gives you is that this is going to be a super hedging strategy, okay? So if you're going to invest this amount into the underlying fund, you're going to pay out this to the policyholder. This is what you have to pay to the portfolio manager. And then this is what you earn by keeping money in the riskless account. And so this is going to be the value of your hedging portfolio, and it's always going to be above the value function of your problem. And it's going to be equal if the W is the worst case policyholder behavior. So in words, start the hedging portfolio with initial capital P equal to P1 plus P2. So don't actually invest everything into the underlying account because you're going to hedge this contract. You have to observe the development of the underlying fund, and you also have to observe what the withdrawal strategy of the customer is. You hold this amount in the underlying fund. You make payments according to this rate to the policyholder. You have to make payments to the fund manager. Keep the rest of the portfolio in the money market account. Pay out this fraction of the underlying account. If the policyholder decides to surrender, this will super-replicate the contract, and it will exactly replicate the contract if W theta was the worst case strategy. Okay, and then the numerical method for this is not straightforward. But let me just say it's a semi-Lagrangian scheme that we do here, and we prove no theoretical results on convergence, but it seems to work. Okay. It's backwards in time. It solves an optimization problem in every time step. It gives approximations to the value function and also to the worst case behavior W hat and theta hat. And then let's jump to the numerical results. So the first picture here is the price of the contract as a function of volatility. Okay, so now I keep all the parameters fixed. I keep the riskless rate fixed, the volatility, the fees that I charge the policyholder, and I'm going to vary one of the parameters just to see what the dependence on this one parameter is. And what you see here is that the price is increasing in volatility. And that's something which we knew from the beginning, right? Because it's like there are all these options embedded in the contract, and the options values will increase if there is volatility. I mean, in fact, if this contract depends very much on volatility, because if volatility is high, there is a high probability that the high watermark is going to be pushed up high, and after that the account is ruined. In which case the option has a lot of value because the issuer of the contract has to pay the withdrawals to the policyholder out of pocket. Then the second picture, which was less intuitive to me, maybe I should also mention that even this first simple fact is not always taken into account by insurance companies that sell these contracts, because a lot, like in the US, these contracts work like, if you buy one of those contracts, you first choose an underlying account. And then you can add options on this account, like a withdrawal guarantee, and you can also add a death guarantee, and whatever you want to you can add to the account. And then for every one of these guarantees, you pay a fee, like a periodic fee, for example. And in many cases, the fee of the guarantee doesn't even depend on the underlying account that you choose. So implicitly, the fee that they calculate doesn't depend on whether you choose an underlying account that has high volatility or low volatility. Okay. Second picture shows the dependence on the interest rate, and so the dependence on the interest rate is low interest rates make the contract more expensive, and that's something that was not immediately clear to me. But it also explains that it makes these products more difficult to sell in a low interest rate environment. Okay, that's also why we maybe have seen no growth in this market from 4 or 5 years ago until now. Then this is the initial price of the contract depending on the periodic fees that I charge on the contract. And that's also clear. If I charge more periodic fees, then I will be able to sell this contract at a lower initial price. Then this is the price of the contract depending on the management fee that I pay, and it's strictly increasing. And so this is a discussion that is a point that is discussed in some of the literature on these products. Should there be a management fee or not? And then if you price according to how I price, which is strictly taking expectation on the risk neutral probability measure, there is no value in having a fund manager. Okay? Because if you invest in one of these funds, maybe you still believe that one fund manager is better than the other because he or she generates a higher mu, which is expected return on this on this account. But this is on the probability measure P. So as soon as I change to the probability measure Q, I don't even see this. Everything is like the return is always R. Okay? And so to you as a policyholder, it might be still worth something to have a good fund manager, to have a high performance under the probability measure P. But if I value this contract on the Q, this Q2 is a pure friction to me. It's just a friction that is going to the portfolio manager. So pricing the contract with this method would just suggest to not hire a portfolio manager and just invest the money in an index or an ETF. And as a side bonus, it will also make the delta hedging easier than if you have to delta hedge a managed underlying account. Okay. So this is Q1 versus Q2. Say I fix the initial payment that you have to make to me to 1 for a unit contract, that I don't charge any additional amount on top of that, and I want to be compensated for the contract purely through regular payments Q1. And so if I increase Q2, how do I have to increase the regular payments that you have to pay me for the insurance, for the guarantees in the contract? And so it's also increasing here. And then the last picture that I have here is price versus this constant kappa, which was how high the penalty for early surrender was. Okay. And so it's clear that the price is decreasing in this kappa, because the higher I choose kappa, the more of a penalty you have to pay me if you surrender early. So the contract becomes less attractive. But then what happens is it's decreasing, but then it levels out around here, okay, which is related to this fact which I showed you earlier. If I choose the kappa high enough, then for the worst, and the threshold was Q1, which is exactly in this example is 0.012 or something. So if you choose the kappa higher than this Q1, the worst case policyholder will have no incentive of surrendering this contract early, so this additional optionality loses value, and then so that's where the price flattens out over there. So these are pictures for price depending on current account value normalized by the running max and cumulative withdrawal normalized by the running max. And this is the hedging ratio. And so these pictures just show you that everything looks pretty smooth, and to justify the assumptions that I made on the value function U, that it has first derivatives and the second derivative is not too crazy. So again, price is increasing in X and decreasing in Y, and the hedge is always long in ST, and this is in contrast to the hedge of a put option. And this is the picture that I already showed you in the middle of the talk. So this is how a typical contract looks in the middle of the period. I think this is 5 years to maturity. The penalty for early surrender is 0 here. That's why you have this large region where you decide to surrender early. If you increase this age, then you will push back this black region. And if you increase it high enough, then this black region will vanish here out of the picture. And then again, these different colors are, okay, here you will withdraw at full speed. And here you will withdraw at the intermediate speed, and then here you will not withdraw. And then people have asked me why the picture looks exactly like this, and I don't understand, except that if you hear it means the current account value is low compared to the high watermark. So there is no hope that you're going to return back to the high watermark and push it higher. So you're just going to withdraw as much as you can and try to ruin the account. Okay. If you have already withdrawn a lot, you might wait a bit, and maybe there is a chance that you're going to push up the high watermark, and so there are considerations like this, but I don't fully understand why this line looks like this and why you have an island here, and so. This just shows, I guess, that this is not an easy problem to solve. I mean, if you wanted to solve this problem intuitively, it's not so easy. Thanks so much.
Thanks for your other questions.
Thank you. I want to ask about the picture. It's really interesting. So this is simulation, right?
Yes.
I was wondering if you change the parameters, you see different pictures or?
Yes, I mean so we changed the parameters a lot, and we tried different finite difference schemes and finite methods, and so the pictures look like this. I mean, similar, yeah.
Do you have any hope or chance of comparing it to real data, or it would probably be very different, right?
Real data meaning prices at which these contracts are sold, right? We haven't done that.
Because you mentioned that the prices are very simplistic in real life, right? So probably be a very different picture.
Yeah, we haven't done it. I mean, so far this is a purely theoretical study. I mean, I can tell you a little bit that some of the papers in the literature, they argue that, the contract that is like a stylized contract, but it's as realistic as we tried to make the contract here in the paper as close to some of the contracts that we actually saw being offered on some of the web pages. And interestingly, so this is one of the most complex contracts that is offered, but is also one of the most popular contracts that is. So in the US, apparently 60% of all the variable annuities that are being sold contain some form of a withdrawal guarantee. And then some of the papers in the literature argue that these contracts are sold too cheaply in the US. And I was having the discussion with Jim, so he told me he bought one. I don't know exactly which contract he bought and if he made a lot of money. But also the price that I calculate here is a super-hedging price, right? And not everybody behaves in the worst possible way. And so the insurance companies, they have statistics how people behave, and then they value the contracts according to this. But then there is, of course, the problem: what if all of a sudden people change their behavior? Also, there starts to be a secondary market where hedge funds start to buy these contracts from customers. But then, personally, I have not looked into real prices.
I can ask you more of this. When you mentioned, this is the worst case scenario, but it's very interesting already. Could you have an idea of how you would combine it with the statistical data, as you say, for an average case scenario?
Okay, so here is my answer to this. So this tells you the super hedging price, and it also gives you a hedging strategy, right? So you can still sell the contract for cheaper if you want to, but then you can still use the same hedging strategy, and instead of making statistical assumptions on what the behavior. I'm not sure, but what I'm saying is this gives you a price. If you want, you can still sell for cheaper, but then still follow the hedging strategy. At least you will be hedged against the behavior of the policyholder.
Other questions or comments? If not, I thank Patrick and all the speakers.